And we know this result. Another result we did in the last class, and probably we proved the result also. So I'm referring my book, I'm seeing my book right now, and I'm trying to see what was the result over there. Okay, so you can also do it at the time of examination. If you forget, you can refer to the book. So if T colon V2W is linear and beta V1, V2 dot Vn is a basis of V, then there is a very good result which I have forgotten. So I'm referring the book. It is RT equal to span of T beta. Span of T beta. So that is span of T of V1, T of V2, T of Vn. It is not important whether you are able to solve this particular, whether you are able to prove this result or not. It is important whether you can apply it in the problem or not. That is important. So carefully see, we need a basis for the vector space V. So here V, here in this problem, V is R3 and W is R2. And beta is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1 is the basis of R3. So, and the transformation T from R3 to R2 is given as T of A1, A2, A3, which is A1 minus A2 to A3. Now I'm going to calculate these things, TV1, TV2, TVN like this. So T of 1, 0, 0, that will be equal to 1, 0. T of 0, 1, 0, that will be equal to and T of 0, 0, 1, that will be equal to okay. So we have calculated all the TV1, TV2, TVN, but we know that from the above result that RT will be equal to the span of these items. RT will be the span of these items. See the above result. Okay. Now this particular set is spanning RT, but you see that if we choose scalars, say A, B, C, and we write A10 plus B minus 10 plus C02, we represent this. We represent 0, 0 as a linear combination of this. We will find that not all ABC are 0. Why is it so? I'm not showing the calculation because it is not important. As we can see 1 minus 1, 0 is a multiple of 1, 0. Multiple of 1, 0, because you can write, I'm writing over here, we can express minus 1, 0 as minus 1 of 1, 0. So these two are linearly dependent. So this implies that I'm writing, probably you are copying, so I'm writing here. This shows that 1, minus 1, 0 and 1, 0 are linearly dependent, linearly dependent. So we can also express 1 0 as minus 1 0. We can express minus 1 0 as 1 0. Both are true, but so either of these two will be omitted from the base from the spanning set, from this set. Okay, so one of these items will becoming redundant. So I'm omitting this minus 1 0 because I'm very much afraid of negative numbers. So I'm avoiding this minus 1 0. You can avoid 1 0 also. Okay, I do not have this much courage. So therefore we write that, so your RT is now becoming span of 0 to. Now you select, sorry, not you. Now we select A comma B from R such that A prime 1 0 plus B prime 0 2 can be is equal to 0 0. 0 0 can be expressed as this. So this becomes A prime 0 plus 0 to B prime, which is equal to 0 comma 0, and therefore A prime comma 2 B prime is equal to 0 comma 0, and therefore this implies A prime equal to 0 and 2 B prime equal to 0. This implies A prime equal to 0 and B prime equal to 0. This implies 1 0 and 0 2 is Li. So since 1002 spans RT and 1002 is Li, so 1002 is a basis of RT, and since this basis contains only two elements, therefore dimension of RT or rank T is equal to 2. Okay, so yeah, also you can write 0 1 was not there, na? So Aniket, 0 1 was not there. I am only talking about this set. I'm talking about these 3 points. In these 3 points, 0 1 was not present. So you cannot write, even if you can write 2 into 0 1, actually I want to see whether these vectors are linearly independent or not. And I want to find out the linear dependency between these vectors. I'm only interested about these vectors. 0 1 doesn't come over here. Okay. So 0 1 is not a part of this game. So rank of T is 2. This calculation has been done to check the redundancy of the vectors present in the spanning set only. So the dimension, this part is done. What was the second? What have we done over here? Part C. Now part D was that we have to check. Part D was that we have to check whether the rank nullity or dimension theorem is satisfied or not. Rank nullity or dimension theorem is satisfied. Okay, so we know that rank of T plus nullity of T, since rank of T has come out to be 2, and in the earlier session we found nullity of T as 1, so their addition will give you 3. 2 plus 1 equal to 3, and we know that this is actually equal to dimension of R3. This is actually equal to dimension of R3. So rank nullity theorem is being satisfied in this particular case. Rank nullity theorem is being satisfied in this particular case. Job done. Next, I'm going to the next page. It is E. I have to check whether whether T is 1 to 1 or on 2. Okay. If you have forgotten the definition of one-to-one and onto, then in Friedberg, in the appendix B, that has been explained. So I am referring that particular chapter to you. You can read it from the appendix. But to show one-to-one, we don't actually need this. Anyways, first of all, let us try. We know a few minutes ago in the last session, I told you that T is one-to-one if and only if null space of T is equal to 0 bar. So if null space of T is 0 bar, T is one-to-one. So this is true. If T is one-to-one, null space of T will contain 0 bar. So it is both way true. So therefore, but according to this, we see that null space of T in our case is actually it is actually A into 1 comma 1 comma 0, A belonging to R, which is not obviously equal to okay, this is not obviously equal, sorry, it is not obviously equal to this because this is the singleton set containing the 0 vector, and therefore null space is not 0 bar. That is null space is not 0 bar of R3, and therefore this implies that T is not one-to-one. T is not a one-to-one function. And you see that for every vector of R2 of the form A1 minus A2 to A3, there exists a vector in R3 such as A1, A2, A3, so that T of A1, A2, A3 is equal to A1 minus A2 to A3. This is true. And therefore, and so, by definition, T is onto. So this transformation is not one-to-one, but this transformation is onto transformation. Okay. So this completes our problem. This completes our problem. So if you have any doubt, you can ask me. If you do not have any doubts, then you can write in the chat box. If you do not have any doubt, I can go to the next problem. It seems that you have no doubt. It's a very good sign. So linear transformation, and someone has written something. 0.3 means which one? I have lost my, I mean, what was 0.3? I wrote two theorems. I wrote two theorems. You are talking about the second one. You are talking about this. This one. Okay, what about this? You want to say that if t is 1 1, then t is on 2. So that's why you are confused. Is this the point of confusion? Okay, so there should not be any point of confusion. I am again writing the statement for you. You tell me what point you are missing. Let V and W be vector spaces of equal finite dimension and T colon V to W be linear. Then the following are equivalent. Number one, T is 1 to 1. If T is 1 to 1, then number two, then T is also on 2. And if T is on 2, then rank of T will be equals to dimension of V. All these statements will hold. They are equivalent to one another. But what you are missing at this particular, yeah, all three are valid simultaneously. Means all three are valid simultaneously. If this is true, then that is true. That is true, then this is true. If rank of T equal to dimension V, then you can say that T is on 2. If T is on 2, then you can say T is 1 to 1. But this thing will not be applicable to the current problem because of this. Here my V is equal to R3 and W is equal to R2. Dimension of R3 is not equal to dimension of R2, as dimension of R3 is 3 and dimension of R2 is 2. This theorem is only applicable when two vector spaces from which the transformation is defined to another are of equal dimension. Otherwise not. Otherwise these statements will not be equivalent. Therefore, in this particular problem, we have got T is not 1 to 1, but T is on 2. Okay, so do not confuse this particular theorem to the given problem. You have to check what vector spaces you are actually talking about. Are they equal dimensions? So the statement, you see, your question, your doubt was very good. I knew that doubt will come to your mind, and it has come. So see, once you read this particular problem, tells us that once you read a particular theorem, you have to be very careful. You have to mark the important points. First important point in this theorem is this should be equal. The two vector spaces are equal. Second important point is finite. If we consider infinite dimension, maybe this result will not hold. This result is not holding for infinite dimension, probably. Otherwise, they could have written, if they could have written that let V and W be vector spaces of finite dimension, of equal dimension. That means what? That means if I do not write the word finite, that means I'm not specifying it. That means it is true for both finite dimension and infinite dimension. But you know a particular vector space which has infinite dimension. So for example, set of vector space of all polynomials whose coefficients are taken from the set of real numbers. So that will be having infinite dimension, whose basis is 1x square dot 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 x to the power n and so on. So this result, when they are specifying it is for finite dimension, that means something is there. Okay. Otherwise, for infinite case, probably it will not hold. We don't know yet. And second important point is that if T is not linear, then this will not hold. This is not holding for any function. This is only holding for linear transformation kind of thing. Okay, so when you read a particular statement, you be very careful. What each and every word is very important. That's why I always ask you to read from good books. Okay, I always ask you to read from good books. And so in good books, they always, maybe less number of problems are solved over there, but they are very much, I mean, careful about stating the definitions, theorem, corollaries, and results. Okay, I found, yeah, Aishik Mathur. Now your question. We have been asked to find the bases of NT and RT. So I have found the base of NT and RT. I showed you in the, so let's talk about RT. RT is defined by this formula, span of T beta, if you can recall. Now what is beta? Beta is the basis of the vector space V. Now your vector space is R3 and its basis is this. Okay, so consider this as V1, this as V2, this as V3. Now you have to calculate TV1, TV2, TVN. Now TV1 is this one by rule, TV2 is this one by rule, TV3 is this one by rule. Now span of TV1, TV2, TVN means span of this, this, this. Now we know that a particular set can span anything, but it will be basis only if it is linearly independent at the same time. A particular set can be linearly independent, but it will be basis if it can span the subspace or the vector space. So we know that this particular set is spanning RT, but we have to check whether this RT is Li or not. If I show that this set is not Li, then it will not span it. But a careful checking has revealed that this vector 1 0 and minus 1 0, they are dependent on one another. Even if you do this calculation, you will find a minus b equal to 0 and c equal to 0. So a equals to b and c equal to 0. Not all vectors are 0. Not all scalars are 0. So minus 0 can be written as the scalar multiple of 1 0. So they are dependent. So since they are dependent, one of these vectors is redundant. You can omit it. So I am omitting the vector minus 1 0 from the picture. Then also RT will be spanned by 1 0 and 0 2. Okay. Now you have to check that these vectors are linearly independent or not, for which I have chosen the scalar quantities a comma b, a prime comma b prime. And by the process of showing linear independence, I have shown that this is 0 only if a prime is 0 and b prime is 0. So that proves that this set is Li, this set is Li, and this set is also spanning RT. So if a particular set is Li as well as it spans RT, a vector space, that becomes the basis of the vector space. So this becomes basis. And so RT's basis have been found, as you have asked me in the chat. The basis of RT has been found. And since the number of elements present in the basis is the dimension of the vector space, so RT has got dimension 2. Here the vector space is RT. So RT has got the dimension of 2. Why RT is a vector space? Because RT, in the last class, we proved that RT is a subspace of R2. Why? Because if T colon V to W is linear, then NT is subspace of V, RT is subspace of W. Okay, so since RT is a subspace of W, so RT is a vector space over the same field R. So therefore basis of RT is this, and the dimension of RT, which is rank T, is 2. I am finding rank T because I have to verify the dimension theorem also. Now rank T has been found, and in null space of T, I'm again considering this point. Null space was coming out as A into 1 1 0, A belonging to R. Now null space of T has been written as a span of this single vector, because it is a linear. What is the definition of spanning set? It is all possible linear combination of the vector, but it is a singleton set, and singleton set is always Li. So 1 1 0 is Li. So this 110 is Li and 110 spans NT. So 110 becomes basis of NT. And since it becoming basis of NT, it contains only one element, and therefore dimension of NT is equal to 1. Now in rank T is 2, nullity T is 1, so their sum is 3, and you know that dimension of R3 is also 3, and therefore it satisfies the rank nullity theorem or dimension theorem, whatever you call it. So understood? Oishik Mathur? Yeah, okay. Now I am giving you a problem. I'm giving you a problem like another problem is there 3 T colon R2 to R3 defined as T of A1 comma A2 is equal to A1 plus A2 0 to A1 minus A2. This is the problem. This is problem number 3. We have to show the same things over here. First of all, you have to check whether T is linear or not. Okay, it is your homework. Do it at home. You are at home right now, so do it after class. Do not waste time. Second is find NT, find RT, okay, find rank T, find nullity of T. Verify dimension theorem, okay, and find whether T is 1-to-1 onto. Now I know that some of you are maybe scanning some of you may be scanning the answers given at the end of the book, but the answer is not there. So I leave it for you. I said that I am considering the easy one for me, and the problem which has no answer given in the book, that is left for you. So this is this is the problem I'm leaving. Can you solve it? Can you solve? If you are looking for the answer in the book, answer is not there. So after this session ends, you don't have to rejoin, but you try with this particular problem because you have 9 minutes 28 seconds left, and I'm pausing the recording and relaxing and waiting for your answer. Answer to the problems apparently, and this although it is incomplete, I have written the answers only, so you just try to do it in a proper way and put an explanation to this particular part. So with this, I'm going to conclude my today's session. I'm not going to rejoin, and hope to meet you on Friday. Okay, we have class on Friday with you. So this much for today. You start doing problems of 2.1, section 2.1. Okay. So bye for now.